Probably the most important operators when dealing with bits are the AND and OR operators. Now, we've seen an AND and an OR before, but we've seen the double AND and the double OR before. Now these are the single AND and the single OR. The single AND and the single OR must not be confused with their logical counterparts. I call those the logical ones, double AND, double ampersand and double OR. Those are the logical operators. These are the bitwise operators. And they are different. They work in slightly different ways. They're very, very similar, but they're actually different. They mustn't be confused. The AND, the ampersand, bitwise AND operator, produces a result such that if the bit is on in both operands, it is on in the result. Now, what does that mean? Well, let's think of an example. So if we call the result, say, Z, and Z equals X ampersand Y, then for each of the bits in Z, let's say we'll test the first bit first. The first bit in Z will be on if both operands in X and Y, in other words the first bit of X and the first bit of Y are both on, then the first bit of Z will be on. And if either of the first two bits in X and Y are off, then it will be off in Z. So it's almost like the real double ampersand, the logical double ampersand, except we're doing it 32 times for each integer, once for each bit. Because if you think about it, those two smaller bullet points you've got in front of you are exactly how the double ampersand works, except the double ampersand works on the entire number, whereas the single ampersand works on each individual bit in the number. If I show you an example of that, which I will in the next slide, then you'll probably have a bit more understanding of what I'm talking about. The bitwise OR operator is almost the same. It's just like its logical OR counterpart. If a bit is on in either operand, it is on in the result, and if a bit is off in both operands, it is off in the result. Okay, I've got to show you an example of that, otherwise you're going to get very confused. 104 and 13 equals 8. Now how could that possibly be? Let's have a look at the bit patterns and hopefully it will all become clear. The bit pattern for 104 is as follows: 0, 1, 1, 0, 1, 0, 0, 0. The bit pattern for 13 is 0, 0, 0, 0, 1, 1, 0, 1. Now the answer will be built up of 8 bits in this case, and with each of the bits in the answer, the bit will be on if the corresponding bit in both of the two operands, 104 and 13, are on. So let me show you what that means. There's only one spot where the bit is on in the corresponding place in both operands, and that's in the 8 spot. In the very first pair of bits, they're both off. In the second pair of bits, the top one's on but the bottom one's off. So they're not both on, so the answer is not on either. In fact, there's only one spot in the entire pair of operands where the same bit is on in both operands, and that's in the 8 spot. Stare at that and you'll see the pattern. It will emerge. See the 1 in the answer? If you look directly above the 1 in the answer, you'll see that the 1 is on in both of the operands, whereas it's not both on in any other bit. As far as OR is concerned, 52 or 12 equals 60. 52 looks like that, 12 looks like that, and the answer is if a bit is on in either of the operands, then it's on in the answer. And that's pretty much all there is to it. Stare at that for a little while and you'll get it. Pause the video if you need to. Now, when we're actually using these, the AND and the OR operator, we typically either are turning on or turning off individual bits. We don't tend to do AND and OR arithmetic like you saw in the previous slide. We tend to just turn single bits on at a time, or we turn single bits off at a time. And if we turn a bit on, we might do it like this. We might define a flag, such as 1 shifted left 3. Now we know that that's just a single bit, the number 1, shifted left 3. So it's actually the number 8, isn't it? Because 1, 2, 4, 8. Okay, so it's the number 8. So it's a single bit turned on, 1 bit. And we might have a integer called status, which is we would think of it as 32 separate flags, 32 separate booleans. One of them, the one in the 8 spot, we're going to decide that that corresponds to whether somebody is married or not. It's going to be a boolean. If it's 1, they're married, and if it's 0, they're not married. So what we want to do is we want to turn on the married bit independently of all the other bits, and we want to be able to also turn off the married bit independently of all the other bits, and we want to test whether the married bit is on or off independently of all the other bits. And this is how we do it. We say status or equals married. Now, what does that mean? That means status equals status or married. Remember how we can expand or equals? It's like plus equals. X plus equals 3 is the same as x equals x plus 3. Remember that? So status or equals married is the same as status equals status or married. Now what's status or married? Well, the answer of status or married is simply the status plus the married bit turned on if it wasn't on before, which is exactly what we want. So we just need to turn on the married bit in status. It may already have been on, and if it is on, then this line will make no difference whatsoever. But if it wasn't on, this line will turn it on. Now, slightly more complicated is turning a bit off. It's a simple line of code to write, but it's difficult to remember sometimes. Status and equals married, and equals tilde married, I should say. The tilde is very important. See the tilde in there? Now, what I will get you to do right now is pause the video and write yourself out an example. Create a random series of bits and call that status. And the married bit is going to be the one fourth from the right. In other words, it's going to be the bit pattern for 8. It's just going to be a 1, 3 in from the right. So it'll be a 1 followed by 3 zeros, and that'll be the end of the bit pattern. Then take the 1's complement of that, the tilde that, and then AND that with status and see what you get. And I promise you, you'll get status with the married bit turned off. That is, if it was on. And if it was already off, then it will stay off. I'll need you to do that by yourself if you want to prove to yourself that that is true, because I'm not going to walk you through it. Finally, it's quite easy to test whether a bit is on or off using an if statement as follows. You can simply say if status and married, and that will return, well, it doesn't actually return 1 or 0, it actually returns a number that's non-zero or 0. And the non-zero value that it will return is, well, it'll be married. It'll be 1 shifted left 3 or 8. So that the result of that if statement will either be 8 or 0. It'll still be treated as true or false, because as you recall, anything that is non-zero in C is treated as true. So 8 will be treated as true. So if the married bit is turned on in status, then this will result as 8. In other words, true. So let me rephrase. If the married bit is turned on in status, then this if statement will be true. And if the married bit is turned off, then you'll get a result of 0, which is false. So that is simply a way of determining whether one bit is turned on or not. Another way of doing it is to test whether it's turned off. Like that, you can say if not status and married. And I would just read that as an experienced C programmer. I would just read that and say if they're not married. Now there's one thing you have to watch out for when using ampersand and or operators, and it's a precedence rule. The ampersand and or operators, the bitwise ones, have a lower precedence than equals and not equals, and greater than and less than and so on. So that can trip you up. You can get into all sorts of trouble. I don't know how many times I've spent searching for bugs that have come from this sort of operation. If status and married equals 0. Now, how you might personally read that is you might say, well, I'm just going to test to see whether they're not married. And that is exactly what the person who wrote the code probably intended. However, that's not how it's going to work. Equals has a higher precedence than ampersand or. So the very first thing that's going to happen on that line is the equals will be evaluated. So first it will test to see whether married equals 0, and it won't. And then we'll bitwise AND that with status. So you'll bitwise AND status with 0, and you'll get 0 no matter what. So that if statement will always be false. So that's something to watch out for. Anyway, let's go and have a look at some code surrounding the ampersand and or operators. I'll show you how to turn on and turn off bits in code. Here is the file called andor.c. This is our employee example again. Remember our employee with structures and so on? And here is the employee structure, and I've simply created some flags for each employee. Now that's an integer, so there are 32 flags available to me. I'm only going to define 3 of them. Those are 3 independent bits. This is 1 shifted left 0, in other words it's just a 1. That is 1 shifted left 1, in other words it's a 2, and that's a 4. So we go 1, 2, 4, 8, 16 and so on through all the bits that we have, or you can just count up here. 0, 1, 2, 3, 4, 5, 6, 7, however you like to do it. So what I'm getting at here is that each of these 3 flags can individually be turned on or off inside this integer. So each employee can thus be either married or not married, manager or not a manager, male or female. Imagine if we had 32 of these flags. In the old system, before we could address each individual bit of an integer, we would have had to create 32 separate integers in our structure, each of which would be 4 bytes long. At the very minimum, we would have had to create 32 characters, 32 chars, each of which would be 8 bits long. And that's wasteful. It's very, very wasteful of space if we're only going to use 1 bit inside each integer. The way we're doing it now is much more efficient. We can fit 32 bits into 1 integer. Now, that might not sound particularly impressive when you're just dealing with structures like this, but when it comes to communications and developing communications protocols, such things are extremely important. I'll give you an example as why. Let's say you've got 2 people communicating over the internet or something, and they're using a protocol, and this structure defines that protocol. And we would have 1 integer here that represents at the most 32 flags surrounding the conditions of each transmission. So you could transmit 32 pieces of information via that field with each transmission. So let's say you've got 3 of them defined, and so you can obviously send 3 pieces of information through that rather than creating a separate integer for each one. Now with communications, you obviously want to keep your communications traffic to a minimum. So packing everything into 1 integer is very beneficial, but I'll give you another benefit. If someone comes along and says, well, now we have a 4th flag, we can simply use the same flags field to store the 4th flag, meaning that we don't have to create another integer in the structure. If we created another integer in the structure, we would be actually effectively changing our protocol. There would have to be a new version of the protocol issued, which would not be backwardly compatible with the previous protocol, and the programs at each end of the communications line would have to be updated. In this way, one person can update his program at one end of the protocol and still keep sending the information to the person at the other end without anything going wrong. If you didn't understand any of that, then I don't mind, because communications protocols are not really part of this course. Anyway, let's move on. Let's see how we can turn on the flag or turn off the flag. So here is where we read in whether they're married or not. We ask them the question. We use interesting use of getChar. I don't know if you've seen getChar used quite like that before, to get a single character from the keyboard, convert it to uppercase and test whether it was a capital Y, and if it was, then turn on the flag, and if it wasn't, then turn off the flag. And that's all. You will not be turning on or turning off any other bits other than the married flag. Now I could copy all that code and paste it again and ask exactly the same question to see whether they're male or female, to see whether they're a manager or not a manager, but I couldn't be bothered. It's just exactly the same code all over again. This time we'd be using a different flag. Again, I suggest that you study that line of code and that line of code to convince yourself that you are comfortable with their workings before you proceed. Finally, when we're printing out the employee, we simply test to see whether the flags field contains the married bit or not. And if it does, then we print out the word married, and if it doesn't, then we print out the word not married. Again, I guess we should test to see whether this works or not. No errors. Run. Please enter your age, 23. Married, yes or no? Okay, let's say yes to begin with. And okay, we successfully got married out of that. Let's try it again, and this time we'll say not married. No, we're not married, and that's working as well. Okay, so we're managing to turn on or turn off that bit. Now, that sequence that I just showed you there, which is testing if a bit is turned on there, and turning a bit on and turning a bit off, they are used all the time in C programming, all the time. It's very, very common. I suggest that you get used to seeing that. You get used to reading what's going on there, because you will encounter it a lot. Okay, let's move on to the next module.